What's up, YouTube? I believe that we're live. Let me confirm. Hell yeah. Hell yeah, 6 9. What's up? SB Practices, Love 1845. Of course I remember you, dude. Welcome. Hey, we got Panayatis too in the chat as well. Thanks for crossing over, everybody. So if anybody's watching the VOD, I just wrapped up my classical guitar practice stream. I'm a software engineer. I used to work at Google. My entire team got laid off. And now I am a practice streamer. So I have a classical guitar stream where I practice classical guitar. And now I'm trying to build this stream, which is a mathematics practice stream. So this is literally the nerdiest thing that you've ever seen. If you haven't seen this already, it's really fun, I think. It's a nice little chill community. I'm going to be practicing linear algebra today, which is one of my favorite fields of math. This is actually the class that changed me freshman year, first semester of college. I took linear algebra, and it converted me from a chemical engineering major to a math major. Then I studied pure math. I love linear because, to me, dude, linear is like actually the greatest math. It is the GOAT. Because, dude, like, linear is the most useful math there is. Everything in math, you just try to convert into, you try to take some complicated, complex type of math, like representation theory, for example. We've got these, like, really complex things called groups and symmetries and all these algebraic structures, and that's complicated. You try to turn everything into a linear algebra problem because we understand linear algebra inside and out. We understand linear algebra. So all of math is just trying to convert even calculus problems like differential equations. The goal is to convert something from a differential equation into linear algebra because this is the only math that we really understand inside and out. So linear is beautiful because it's the most useful math there is, but it's also the beginning of proof-based, pure theoretical math, like vector spaces and things like that. So, like, linear algebra has a soft spot in my heart. I love it. And so nowadays I'm just practicing math for fun on the internet. And I'm trying to show, in some sense, what I'm trying to convey to people is that you can study math for fun. Like, I'm not going to be a mathematician. I gave up on that dream a long time ago. Dude, like, I gave up on that dream a long time ago, and then I went into software, and I had a good career in software. Nowadays, like, dude, I'm not trying to become a mathematician. I mean, maybe I might want to, like, teach, like, high school math or something, but I don't need to study linear algebra to do that. I don't need to study, like, advanced abstract algebra or something to teach high school math. Like, dude, I'm studying this for fun. I am studying advanced college level math just because I love it, just because it's fun. And if you ask your math professors why they became mathematicians, it's because they think it's fun. Like, that is the reason to become a mathematician. It's because it's beautiful. It's fun. Like, yeah, it might be useful, but probably not in your lifetime. Like, dude, seriously, like, mathematicians who are studying pure math, they don't expect their math to be useful in their lifetime, to solve any real world problems. For the most part, this is all an exaggeration, kind of, but it is directionally true. Like, you study math because it's fun. It's kind of like Sudoku. Like, if I'm on an airplane and I don't have an internet connection, I'm going to do a Sudoku, or I'm going to crack open a textbook in math, and I'm just going to solve some problems. Like, that's not a joke. I actually did math for, like, 4 hours straight on a plane, like, just a couple months ago. Like, I'm not exaggerating. Like, I was on a plane, and the entire time I just was solving math problems. No internet connection, no TikTok, no YouTube, no nothing like that. Just paper, dead trees and a notebook. Like, it's beautiful. It's wonderful. Math has been around. We're still studying arguments from thousands of years ago. Like from the Greek mathematicians, we're still studying their arguments from like Euclid and, you know, the Euclid is just the best example. But like, we're still studying arguments from hundreds or thousands of years ago. Like, it's going to survive ChatGPT. Like, dude, studying math for fun is going to survive AI. Like, AI is not going to take away the love of math, especially studying math for fun. ChatGPT is not going to take this away. All right, so there's my little monologue. I hope you all enjoyed it. Now let's get into the practice session. So, you know, who knows? Who knows what happens in the future? We may become like sleeping cats and we don't have anything better to do than to just entertain ourselves because the AI has taken everything. And if so, what's going to be your hobby? My hobby, the way I'm going to fill time and find meaning is by studying, just learning as much as I can, even in my little, you know, pink, mushy, human biological brain. So there's my little rant for today. I hope you all enjoyed that. I need to find my iPad. I'm struggling here. Y'all. Okay, so sorry, I wasn't ignoring the chat. I just wanted to give my little monologue. What's up, Bloodfire? Welcome back, dude. Welcome back. Axel Blaze. Dude, you're Tom, right? Bro, Tom? Thanks for making it. Yeah, Tom, dude, good to see you, man. Good to see you, Tom. Tom used to be a private student of mine. Dude, how is math going for you, bro? And I love that there's a couple of people here. Panayotis and SB Practices. What's up, y'all? Welcome to the practice stream. Panayotis over here is apparently shooting for 2,700 ELO in chess. Dude, like, I didn't know I have, like, a chess grandmaster watching me. Like, what the hell? Like, y'all, yeah, please drop out. Like, y'all are gonna go play some chess together? Don't watch me. Go play chess. Dude, if you get an opportunity to play chess with, like, a legit almost grandmaster, yeah, what are you doing watching me? Like, go... Dude, that's insane, man. That's so cool. Hell yeah. So there should be some background music. Damn, 8 people watching now. Yeah. Hey, we got Heidi in the chat too. What's up, y'all? We got Love. Hey, this is fun. It's nice to get like a busy math chat. All right. It's fun to get a busy chat room. Now let's clear the room. Let's get really nerdy. I think I want a prestige. We're gonna start over in linear algebra. We're gonna prestige. Why didn't it work? I thought it would already... Oh, I need to like double click another thing. Where is the thing? What? It's still not working? Okay, 1 second. 1 second. I just gotta turn it off and turn it on again. Oh no, a magician never reveals his tricks. That's how I'm doing this. This app called Air Server. If you have a Mac and an iPad, it's a great way to get your iPad on the screen. All right, so what's been going on for the last month or whatever? We've been just solving a lot of problems from Frale. Look at how beautiful this is. There's 144 pages now in this. There's 144. Can you see in the bottom right? There's 144 pages of math. Like, dude, this is so nerdy. Yeah, so yesterday we were working some eigenvalue, eigenvector problems. Eigenvalue, eigenvectors are about if you have a matrix A, like, I don't know, a matrix A, 1, 2, 3, 4, you can multiply a matrix with a vector. Whenever I have to pick some numbers, I use 1, 2, 3, 4, 5, 6. Right? So let's multiply, we're going to have to do a little bit of calculation here, but 1, 2, 3, 4, 5, 6. How do we multiply a matrix with a vector? 1, 2, 3, 4, 5, 6, right? Okay, let me show you how it works. You take the dot product of a row and a column, okay? So what this is you take the corresponding numbers and you multiply them together. 1 times 5, and then you add them all up, plus 2 times 6. 2 times 6, okay? And then we're going to do these. So we've got 3 times 5 plus 4 times 6. Okay? And now, well, that, if we recall arithmetic, that's going to be 12, 17, and 24, 39, right? 39. Look at that. 24 plus 15 is 39. So, all right, there's an example here. And now let's get to the next level here. So if I counted maybe by, let's see, we're going to all the way to 39. Let's count by 5s. 5, 10, 15, 20, 25, 30, 35, 40. So on the axes, I'm counting by 5s. 5, 10, 15, 20, 25, 30, 35, 40. Okay? So all the way up here is 40. This is 5. Now, if our original vector is 5, 6, so that's going to be just about right here. Okay? So we have this vector, v. Well, I called it x. We have this vector x, and then after multiplying it by this matrix, multiplying it by that matrix, our new vector is 17, which is going to be like right about here-ish. 17, 39, which is almost 40. So here, look at this magic. Look at this magic trick over here, y'all. Check this out. Whoop, whoop, move that, scooch that right over there. Try doing that on a chalkboard, y'all. Okay, so right about here is, let's get like a little parallel line, and down here, right about there is our new vector. Let's give it a different color. Let's erase these red marks. Oops, a little too much. Okay. I'm struggling. All right, slow down, John. Slow down, John. Something like right about here. This is the new vector. Okay? So this was our matrix A transformed our vector to a new vector. It really lengthened it, and it rotated that vector. It has a different angle now. So that's an example of something called a linear transformation. Linear transformation. By a matrix A. So we had one vector, and then now we have a new vector. The type of math that we were studying yesterday, we were asking the question, when can we describe when we don't have any rotation of the vector, but we just scale it to a new spot somewhere. So I'm just going to say, maybe this is our original vector x, and maybe A stretches it to be, but it's still on the same exact line. So now this is a stretching maybe it's like 2 or 3 times x. This is like around 3x. So if you triple a vector, it stays in the same angle. It stays in the same direction, but the length is longer. It's just stretched. What is lambda for? Good question. So that is, I'm just saying, sorry, I've been missing chat. What's up, everybody? Thanks for tuning in. Y'all, it's nice to have a few people in the chat today. Y'all. So what's up? It's good to see you all. What is lambda for? So this is our question. Like, when? We want to know, when does A just stretch / shrink? This is our question. When? Like, can we understand when this happens? That a vector is just stretched or shrank, or, kind of reflected in the other direction. Maybe this one's shorter, but it's still in the same line. It's still the same angle. It's just flipped over, but it's still on that same line. This is still the same line. All of these are still on the same line, but there's no rotation at all. When does this happen? These are called... When this happens, this is called an eigen... This thing is called an eigenvector, and lambda is called an eigenvalue. Okay? An eigenvalue and eigenvector are special vectors and scalings the word is scaling instead of stretching / shrinking. The word is scaling. Like, when does a matrix scale a vector? So this is what we were studying yesterday, and this is just like a little review, or just kind of giving a flavor. If y'all want to check that out, the stream yesterday was pretty fun, I think. But today, y'all, we got a few people in chat. Some people were asking, what the hell is linear algebra? Let's prestige. So we were working on chapter 1, 2, 3, 4. I think yesterday was 5. Today, let's reset. Let's go back to 1. And then once we get done with all this, then let's do 6. And then once we get done with that, then let's loop back and then do 7. Does that make sense to y'all? Like, this, strategy? Let's just keep prestiging. Let's go back, once we get to 8. How many chapters are in this book? Yeah, yesterday was 5. That's amazing to me that you even know that. That's amazing. All right, 10. There are 10 chapters. Okay, so here's our strategy, y'all. This is Frale, right? Here's our strategy. This is Frale. This is linear algebra. Once we get to 8, then we'll get to 9, and we prestige. Once we get to 10, we'll prestige one last time. We'll do it all again. And then, only then, are we going to go somewhere else? I don't know yet, but this is another book. Okay? And then we'll keep prestiging and adding a new chapter of a new book, a new subject, maybe calculus, maybe linear algebra 2, like year 2 of linear algebra, like Axler. It could be Axler, for example, for like more proof-based theoretical linear algebra. Or we could go to like abstract algebra. Instead of linear algebra. I don't know. Representation theory? We could go to freaking representation theory next. But I feel like we need abstract algebra before representation theory. So we shouldn't do that. We shouldn't go that far. But I think it could be valid to go to calculus. You know what I mean? Bro, I have an AI exam coming up, but it is just very basic, or you can help me with it. Yeah, feel free to shoot a question in the chat. If I get bored, I might answer it, but yo, dude, good luck on your exam, hell yeah. All right, let's do this. Let's prestige. We're going to go to Frale. We're going to restart chapter 1, section 1. And we're starting from the beginning. So for those who have found the stream recently and are curious about linear algebra, well, here's your chance. Let's start from the beginning. Vectors in Euclidean spaces. This book is so beat up. I love it. Frale 1.1.6. Oops. This is about vectors in Euclidean spaces. All right. Any questions? Any thoughts? How do you all feel about this idea? About a math stream in general. Also, let me try to... Can I get chat up? Yo, there it is. I got chat. But that's yesterday's chat, right? What's going on here? Oh. I know what's going on. Wrong chat. That was chat for the wrong channel. There we go. All right, we got chat. We got chat and everything. What's up, y'all? Panayatis demolished me. I absolutely loved it. Dude, I'm happy to hear that. I'm very happy to hear that. That's awesome. Like, I wish I had the free time to try to pursue chess. I don't. Not yet. Maybe in retirement I might try to learn chess, but not at this stage of my life. Alright. I think that looks decent, right? Haha, good game. Okay, well, you all missed my crazy rant. I was trying to give like a little... So, since you were away, I gave a little introduction to matrix multiplication. I showed how this vector was transformed to a different vector, and that what we were doing yesterday was thinking about eigenvectors. Like, when is a vector just stretched or scaled by a matrix? So, and then I said, let's prestige. We're restarting because there's new people in the chat who are here for the first time. We got to chapter 5, and now, instead of going to chapter 6, we're restarting. Let's start at chapter 1. Once we get through chapter 6, then we'll reset. Then we'll get to chapter 7, reset, on and on until we get to chapter 10. And then once we get through chapter 10, we're going to start another book. And we're going to keep resetting and keep doing this again and again and again forever until we die. Let's go. Frale 1.1.6. Let's say, let Sorry for the dark joke. I know dark jokes happen sometimes here. U is -1, 3, -2. V is 4, 0, -1. And W is -3, -1, 2. And it asks, what is U plus 2 times V minus 4W? Okay, well, all right, vector addition, multiplication. This one's a little more complex than the other ones we were doing before, but this is going to be U plus 2 times V. I'm going to substitute one at a time, like little bits by bits. What is 4 times W? Well, you multiply every number by that scalar. So I'm going to multiply -3, -1, and -2 all by 4. I guess I still have the minus sign on the outside, so we're just going to quadruple each of those numbers. Let's keep red just so you see it. Quadruple, so that's -12, -4, and 8. Right? Boom. Now, this is going to be U plus 2 times V minus that other stuff. Well, let's just pause for a second and simplify this. Let's distribute that negative. 12, 4, -8. This is going to be the same as U plus 2 times. Now, if I look at V, remember that this is V, and we add with this other one, right? So if I add those two together, then this vector is now, well, if I only have one vector, I no longer need the parentheses. Adding those two vectors, we have 16, 4, -9, right? And now, this is going to be U plus, let's double all those numbers, 32, 8, -18. And now, last step here, let's pick a new color we haven't chosen. Remember that this is U, right? So let's add these two together. We've got 32 plus -1 is 31. 8 plus 3 is 11. And -18 plus -2 is -20. This should be our answer. Is this an odd? No, this is an even problem, but I feel pretty good about this one. I think that that's correct. I'm so happy that y'all played chess together. That's super cool to me. This is the nerdiest stream on the internet, yo. Like, most people are playing video games, and they're playing, like, Diablo or something. Dude, this is the nerdiest stream ever. Like, we're finding people who want to play chess together. That's awesome. Speaking of chess, I think John Yang plays chess, actually. Like, I'm just saying, I don't know. This is so nerdy. Like, it's so niche. I'm never going to have thousands of people watching me do math on the internet. I'm never going to have, like, a huge audience of people, like, learning math with me. I'm never going to have the audience of, like, a video game streamer. But, like, hey, that's pretty cool. Like, that people are playing chess together. This is so nerdy. All right. Y'all keep chatting amongst yourselves. Chat chess strategy. That's so freaking cool. I mean, I'm also a gamer, so I feel called out. I apologize. I don't mean to be offensive. I'm a gamer, man. Like, I have a gaming stream, dude. Did you know that? I actually do have a new gaming stream. I don't mean to be offensive there. JC Practices Gaming. It's a brand new stream, but I play music games, like music video games. Do you sometimes play with yourself, or you only play with math? Nice to meet you. Nice to meet you, BNA Yazide6723. How's it going? Welcome to my stream. All right, that was Frale. That was section 1. Now we're going to mark that in pen. Done. Solve that problem. Let's move to section 1.2, the norm and the dot product. Let's get another concept. 1.2.6. Now this is a new concept called the norm and the dot product. Okay, let me give just like a rapid fire TLDR. If you have a vector, then the norm of the vector is the length of the vector, right? So here, this creates a right triangle, right? That creates a right triangle. So then, in this case, the length of V is going to be the square root of, in this case, x squared plus y squared. Say that V is x comma y. Then remember the length, the hypotenuse, is by the Pythagorean theorem, by Pythag. That's x squared, square root of x squared plus y squared. We do basically the same thing for higher dimensional. It's the square root of the sum of squares. So that's the norm. And now the dot product. It's a little harder to draw a picture for this, but it's harder to draw a picture even though there is an idea of a picture. A dot B, it's kind of like we multiply these two. I'll give a two-dimensional example. A dot B is going to be A1, B1. So you multiply all of the components together. It's kind of like a vector multiplication, but it's a little different because you multiply those components and then you add them all together. So, sneak peek in the future, remember, if we have a matrix, what we were doing earlier, to do matrix multiplication, you do the dot product of a row and column. This is the beginning of the dot product. This is what I was talking about. You multiply the first number of the first one and the first number of the second. You multiply the second number of each, the third number of each, and then you add them all together. Okay, cool. So there's our little quick intro to those. So, Frale number 6. Number 6 is asking for the norm of 4/5 W. Okay? Well, one thing is I don't even need to look up W yet. I know that a scaling factor commutes, or like it's associative with the norm. So I can factor out or just move that damn, scaling, that coefficient, let's say. I can factor out that coefficient outside of the norm. And at this point, I can look up what is W. This thing says that W is -2, -1, 3. -2, -1, 3. Right? So this is 4/5. And then the length of -2, -1, 3. -2, -1, 3. And as I said earlier, this is going to be the square root of all the components squared and then added together. So, knowing that sounds pretty familiar to this whole dot product idea, right? Oops, we're running out of batteries. Because we're like squaring numbers and we're adding them all together. That is that the norm of a vector x is the square root of x dot x. The dot product of x with itself and then taking the square root of that. So this connects these two different ideas. Okay. Continuing on, don't get distracted, John. Let's keep going. Is that right? I think that this should be. I think that you can factor out the scale. Yeah, you should be able to. I think so. 4/5 square root of. Yeah, I got this wrong. 13, 14. And then, well, I think that's it. Square root of 14 doesn't simplify at all because 14 is 7 times 2, and those are prime. All right. This problem is even, so we don't have an answer in the back of the book, but I feel pretty good about that. Correct me if I'm wrong, anybody who's watching the VOD, but I'm pretty sure that that's right. Next, mark that in pen. Never work that problem again. We did it. Number 1.3. Let's do C minus D. Pencil? Yeah, I'm so annoyed by the pencil marks. Okay, so now, Frale. This is my favorite book in linear algebra, and nobody talks about this book, but it's my favorite. I own String, I own Axler back there, I own Shilov as well, but like, I'm telling y'all, Frale is the best introduction to linear, I think. 1.3.5. Where are we now? This asks us, what is C minus D? Where C is 2, -1, 0, 6, -3, 2, and D is -4, 2, 3, 5, and -1, -3. Then C minus D is going to be, well, let's Let's do this. This is neat. Oops. Duplicate. That's what I meant to do. Duplicate. Erase D. Add a little minus. And scooch this thing. So those two subtracted. Then we just add and subtract the corresponding numbers in each component of these matrices. So 2 minus, if I do 2 minus -4, I'm just going to highlight this first example. 2 minus -4 is 6. Right? And then -1 minus 2 is -3. 0 minus 3 is -3. 6 minus 5 is 1. -3 plus 1 is -2. And then 2 plus 3 is 5. Got it? Okay, that's C minus D. I feel this is an odd-numbered problem, and Frale has answers to most of the odd-numbered problems. So on this one, I can make sure, that I didn't make a silly little error. And let's take that opportunity. Number 5. 6, -3, -3, 1, -2, 5. We got it. Verified, correct. Let's move on. .4. JK, it's motivating me like crazy that y'all are talking about math, or are you motivated by the chess? Dude, this makes me so happy that y'all are like chatting about chess with each other. It's so cool. Sorry, I'm not like reading the chat that much. I'll take a break between the math problems and catch up with chat when I'm here. Y'all are talking about squatting too? All right. Anxiety is going up. Why is that? What are y'all talking about? Oh, video. Yeah, if y'all are talking about video games, dude, I play rhythm games. I play Rhythm Doctor. I also play board games. I play hella board games. Y'all, board games? ChatGPT is not going to take board games, dude. Like, AI slop, is not going to make board games over the table with a dinner party. Invite friends over, cook some food, play a board game together. Where is it? I don't know where I put it, but I have this amazing game that I'm a geek about, y'all, right now, called Earthborn Rangers. Dude, I'm geeking out about how good this game is right now. I'm a huge tabletop geek. So I have that gaming channel, and I'm thinking, primarily it's music games. Someday I also want to do board games, tabletop games. Dude, the nerdiest people I know all play games, tabletop. Alright, so I'm just gonna skim all this chat. Y'all, it's good to be chatting with you all. It's nice to have an audience while I study math. Are y'all enjoying this? And yeah, I was thinking, somebody mentioned the dot product equation here. Yeah, dude, MK, good call out. You're absolutely right. Right here. A dot B is norm of A, norm of B, cosine theta. I thought about mentioning that, but I was like, I'm just going to leave that for whenever it comes up in actual problem. I thought of, because I was just trying to give a quick little intro over here, and I was like, that would take a little longer to explain, and I'm not ready to draw that picture and stuff. But yeah, you're totally right. I thought of that too. Wait, bro, Panayatis, you're 15 and you have 2,700? Oh no, but you're 2,100, but still, dude, Panayatis, You're 2100 at 15? That's crazy. Congrats, dude. All right, catching up. 2100 brown belt, no Olympiad, and 9 years of guitar. 9 years of guitar. What are you working on? So anybody who's only here for math, I also have a guitar channel called JC Practices Guitar, and that's where most people know me from. Hell yeah. Yeah, just reading. Olympiad, y'all. Oh, you're working on Asturias, Catedral, and La Campanella? Dude, that is awesome. Yeah, I'm working on Asturias. You know that, right? Did you see my Asturias today? Yeah, dude. What do you think? Any feedback? Anything I could do better? Like, dude, feedback is a gift, everybody. I keep saying that in my guitar stream all the time, and it really is true. Feedback is a gift. So if anybody has any tips, like, how can I make this an amazing stream? How can I freaking, do better? How can I do better? I'm not the one to give you feedback. Well, thank you, but still, anybody can give feedback. That's also very important too. That's important in the culture of my streams. Anybody is allowed to give feedback. Everybody should feel encouraged to give feedback, actually. All right, let's go. Some of my favorite and really easy pieces. Oh, yeah, please share. Okay, well, that was Frale 135. Let's go to Frale 14. This is where I would introduce. This is how I would teach linear algebra. I would start with this section. Frale 14, solving systems of linear equations. So anybody who's new in the chat, like, why are we working with blocks of numbers and stuff? Like, what's going on here? Dude, it's because of this, all right? Okay? Dude, in regular algebra that everybody takes, sometimes you end up solving problems like this. You have two equations and you have two unknowns, right? Let's give this one the color yellow and let's give this one the color red. So if we remember mx plus b as the equation of a line, or we could convert this to point slope form or whatever, but we would see that this yellow can be rewritten as y equals negative 1/2 x plus 3/2, right? So that's going to be plus 3/2. The y-intercept is at 1.5, and the slope is negative 1/2. So this is going to look like a line that looks something like this. And then the second line, we'd have y equals negative 4/5 x plus 6/5, right? So that's also a y-intercept that's just like a little bit above 1. So hey, this is actually kind of a not great example to use right now, but it is what it is. And it's also, this one is more, it's much closer to negative 1. but it's like a little bit elongated. The line is going to look something like this. It doesn't matter exactly what it is. But my point is, we can algebraically solve based on these two lines. They are going to cross at some point. They're going to cross at some point, and somebody solved it already for me. Thank you. Awesome. X equals -1, y equals 2. Hell yeah. And so in the regular way of solving these equations, you would isolate one variable. I see that x would be the easiest one here. I would see x is equal to 3 minus 2y, and then we would replace that in the other equation. So let's substitute in 4 times 3 minus 2y plus 5y equals 6, right? This is like a form of algebra that most people have seen in in high school algebra. And then we go through the calculations, and we get -8 plus 5 is -3y. And then we have 6 minus 12 is -6. We solve y equals 2, right? We get that, and then we substitute that back in to this other equation to get x equals 3 minus 2 times 2, right? And, well, what is 3 minus 4? -1. So then we get, finally, our equation, xy is -1, 2. So I got to the same answer that somebody in the chat got to. Thank you, dude. Thank you. So this is like the old school, original way that you learn how to solve systems of equations. But that's in two-dimensional space. A lot of the problems that we want to solve are not in two-dimensional space. They might be in three-dimensional space. You might solve some problems by hand. It's worth doing once or twice in your life. But dude, the real problems that we're solving like today with computers and stuff are not three-dimensional space. They're like 3 trillion dimensional space. Like, imagine that you had literally 3 trillion equations and 3 trillion variables. You would never do it this way. This is a pain in the ass. You would never do it this way, even if you were a computer. There's got to be a smarter way. The smarter way is with matrices. This system of equations, forget about x and y. Like, we could call them alpha and beta, we could call them x, y, we could call them a and b. We can use whatever letter we want to. What matters are these coefficients. 1, 2, and the right-hand side is 3. 4, 5, and the right-hand side is 6. We can solve this system of equations exactly the same. Oh, my iPad is dead. Sorry about that. I should have... I knew that was going to happen. Wow, amazing. Thank you. Well, we got to charge the iPad. Bro, what's up? How's it going, Kashal? Here's a chance to say hi and chat. What's up, everybody? While we wait for my iPad to come back. How's it going? I hope you all enjoy this. We use Kramer's rule because it is better than Gauss-Jordan method. No, it's not. Kramer's rule is super inefficient, dude. Kramer's rule is not. No, you're just straight up wrong. You're wrong, dude. You're wrong, and I'm offended. Get out of here. Get out of here. This is MKO1. No, Kramer's rule is inefficient. It's actually inefficient compared to Gauss-Jordan. But yeah, thank you for calling it out. What I was just doing is called Gauss-Jordan method. Kramer's rule, you can solve these equations with determinants, but solving a determinant is just as many. It's on the same order of computation as Gauss-Jordan. So solving all of those determinants is just as computationally efficient. Gauss-Jordan is computationally more efficient, actually. Like, that's a mathematical fact, dude. Yeah, like, Kramer's rule, I don't even think my class taught. I think my class skipped Kramer's rule. But it is interesting to know, and it can be partially a motivation for determinants. But you have to learn about determinants and other things. What's cool here is that you can teach somebody Gauss-Jordan without teaching them about the determinant. I just want to show that what I did here was a substitution method, but there's another method called the elimination method. The drumming caught me off guard. What drumming? Drumming? Oh, was it me tapping against my iPad or something? I don't know what you're talking about, but yeah. All right, we're back. Do we have background music going? We should have Yeah. How do you all feel about this annoying lo-fi music? I could get classical guitar in the chat. I used to play my own classical guitar in the background, but yeah, I don't know what drumming you're talking about. Would you all prefer this lo-fi, or would you prefer classical guitar by a hobbyist? I think that the guitar people have heard enough of me playing guitar that it's like nice to have something different here. But I could be wrong. You want guitar? Okay, dude. If there's one person who wants guitar, I'd rather play my guitar, of course. But now I'll have to go. Okay. Dude, Panayotis, it's been a pleasure hanging out with you today, man. I hope to see you again soon. Let me know if you enjoyed this. I started tapping. Yeah. So I studied math. What's up? This is MKO1. I have an undergrad degree, a bachelor's degree in math. I basically did a whole master's degree in my undergrad, but I didn't get the piece of paper or anything. The guitar wood sound, is there a particular name of that? I don't know what you're talking about. Was it this? I don't know what tapping... I don't know what you're talking about. Take care, Panayotis. Okay. So I'm trying to teach, just like for a moment, this idea of the Gauss-Jordan method. Percussion. Sorry about the tapping. Yeah, I was drumming. Drumming is the right word. Yeah, that's what I would call it, drumming. Against the desk. 1, 2, 3, 4, 5, 6. So this is called Gauss-Jordan, and we're just going to do the exact same steps. We can add and subtract and multiply these equations. Like, for example, this first equation, I can quadruple it. 4, 8, and then quadruple 12. There we go. Because this equation is exactly the same thing. If I multiply the whole equation by 4, this is the same equation, right? So you can think of, I just quadrupled the first equation, and then maybe here let's do it one step at a time. Now I can subtract the first equation from the second equation. Maybe 4 minus 4 is 0. Let's keep this first one like this. Or let's bring it back. I'm just trying to teach right now. I wouldn't do this exactly this way if it were me, but for the sake of teaching, So divide by 4, we're back here again. But 4 minus 4 is 0, 5 minus 8 is negative 3, 6 minus 12 is negative 6, right? And this is similar or something to, if I divide the second equation by negative 3, then this is 0, 1, 2. Now, let's start getting used to seeing it in one step. Here, I'm going to replace the first row with row 1 minus 2 times row 2, where this one is row 1 and this one is row 2. So if I subtract 2 times row 2, then we have 1, 0, and 3 minus 4 is negative 1. Now, this, if we go back to writing our x's and y's, this means x equals negative 1 and y equals 2. We got to the same exact answer as before, but like, dude, just look at this, all of this of what I wrote over here, and compare that to this. Somehow, this just felt easier. This felt more methodical. This felt more... It just felt cleaner, more organized, easier to do. And it truly is how computers can solve huge equations so much faster. Hey, take care, MK01. Dude, it's good to see you. I'll call you MK. Man, this is high school maths in Asia. Oh, this is high school math. Totally. But I'm just giving like a little brief intro right now, just to motivate for people who haven't seen this stuff. All right, let's keep going. This is totally high school math. I'm trying to connect linear algebra to high school math. You're absolutely right. Now, the real problem that we're going to solve is Frale 1. We're in chapter 1, 1.4.6. Now, this is asking A, reduce to row echelon form, B, reduce to reduced row echelon form, C, find... Oh, that's it. Okay. All right, so I'm not going to explain too much. I'll explain as we go what those words mean. But we have the matrix 0, 0, 1, 2, negative 1, 4, 0, 0, 0, 0, 0, 0, 1, negative 1, 3, and then 2, 4, negative 1, 2, 4, negative 1, 3, 2, negative 1. Okay? So now this is already much more complicated. Like, we've got 3 equations, but now we have 6 unknowns. So just already, right off the bat, this is harder. Like, imagine solving something with 6 unknowns. That gets really complicated fast. Okay, so I'm going to swap these rows. I'm going to write that third one first. So, and I want to write the first row in the second spot and put the second row in the third. So all I did was just rearrange the equations. Okay? And now, voila, we have, this is in row echelon form with 3 pivots. This is row echelon form. This is 1 row echelon form, because row echelon form is not unique. Row echelon form is not unique. That's important to know. but reduced row echelon form is unique. So now we're going to keep going. 0, 0, 0, 1, negative 1, 3. I think we're going to leave that row alone. And now we will subtract 2 times that from the second row. So row 2 prime is row 2 minus 2 times row 3. So yeah, now we have 2 minus 2, negative 1 minus negative 2, which is the same as negative 1 plus 2. And then 4 minus 6 is negative 2. And now I'm going to go ahead and say that row 1 prime is going to be row 1 plus, I'm going to go ahead and use row 2 prime. So notice that I figured out the second row here, the new second row, and I'm going to go ahead and already use this one to modify the first row. 2, 4, and I add negative 1 plus 1. Notice that I'm looking at 2 different... I hope that's okay. Like, I'm kind of trying to take shortcuts here. 3 plus 0 is 3. 2 plus 1 is 3. Negative 1 plus negative 2 is 3. All right. Here we go. We're getting somewhere. Reduced row echelon form should have 1s in all of the pivots. So we need to divide this first row by 2. And then voila, this is reduced row echelon form. Reduced row echelon form. Nothing is unsolvable for the bro. No, dude. Yeah, lots of things are unsolvable. I guarantee you will see me get stuck many times if you hang out here. So this, remember that reduced row echelon form is unique. But reduced row echelon form is not unique. Okay. This was an even problem, so I'm pretty sure that it's right. I can't check the back of the book, but I'm pretty sure that was right. And yes, if somebody was asking, is this unsolvable? I think that they mean, is this matrix unsolvable? Actually, no, there's probably infinitely many solutions. Unless there are 2 contradictory equations. It could be a, like, I don't know. If we have the equations 1x equals 1, and then another equation that says 1x equals 2, this is impossible. Right? This is a contradictory matrix or something. Nah, man, you're a genius. That's not true. Thank you. I mean, that flatters me, but our syllabus only contains 3 by 3 square matrices. Dude, fuck your syllabus, dude. Fuck your syllabus. Because, you know what? You're living in, like, high school land right here, but bro, ChatGPT land lives over here. ChatGPT land lives in 3 trillion dimensional space. Like, yeah, that's what we're learning now. You know, I'm going beyond your syllabus. You can learn a little more. So, like, already here, this is already more complicated. We've got 6 variables. But a computer, literally, ChatGPT is just multiplying giant matrices like this. For my puny human brain, this is a huge matrix. This is a humongous matrix. And it's really annoying to multiply two of these. ChatGPT is actually multiplying 3 trillion dimensional matrices. Like, that's the neurons in the weights of a large language model. So, done. We did it. Frale 1.5. We're going to get to inverses of square matrices. All right. Are y'all having fun? I think that this is fun. I get to study math with an audience. Dude, I get to study math with people and hang out with people while I just study math to fill my abundant free time. 1.5.6. This is inverses of square matrices. Inverses of square matrices. Okay. Heck yeah. Number 6, we've got A. Find the inverse if it exists. B. Express as a product of elementary matrices. All right, so I apologize for insulting your syllabus. Your syllabus is chill. I'm just joking, dude. I apologize if I offended anybody. Good night, sir. You have an English final tomorrow. You're watching math, even though you have an English final. It's funny. All right, cool. So A is, in this case, 1, 1, negative 1. Somebody mentioned 3 by 3 matrices. 2, 0, 3. Negative 3, 1, negative 7. Negative 3, 1, negative 7. The game that we're going to play is A, and then we adjoin the identity matrix, and we're going to do row operations, if possible, and we're going to try to get to I on the left-hand side and A inverse on the right-hand side. So this is the game that we're going to play and see if it works or not. 1, 1, negative 1, 2, 0, 3, negative 3, 1, negative 7. Adjoin 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So again, what are we doing here? We are trying to get to reduced row echelon form. If the reduced row echelon form of this combined matrix has the identity on the left, then what's on the right is the inverse matrix. So this applies the ideas that we did in the other problem. Okay, we've got now, I'll keep that first row the same, 1, 1, negative 1, 1, 0, 0. Let's subtract 2 times the first one from the second. So, so if we subtract 2 times the first row from the second, looking at the right-hand side, we got that. And then 2 minus 2 is 0. 0 minus 2 is negative 2. 3 plus 2 is 5. Right? And now, since this wants it as a series of elementary matrices, the first operation that we did was subtract 2 times the first row from the second. And then what are we going to do here? All right. Y'all, how are you all doing? Thank you for hanging out with me while I do math. It's fun. Sorry for coughing. I'm still sick. 3 weeks after I started getting sick, I'm still coughing. It's pretty annoying. The syllabus that India follows deserves some insult. Oh, really? I learned differential equations, integration vectors, and 3D, but no one ever told me about number theory. Bro, for real. Like, dude, I mean, it's the same here. It's because your syllabus is focused on engineering math. Like, differential equations, integration vectors, and 3D are all very useful for engineering, for, like, chemical engineering and stuff. But, like, nobody gets to show you pure math. Like, number theory is not very useful in the real world. Number theory is pretty much useless to engineering math. But nobody ever experiences pure math. Math for math's sake. Math for fun. Like, I like to call it just math for fun. That is number theory. Like, people who study number theory study it because it's beautiful, because they like it. They don't study it because they can solve engineering problems. Number theory is not useful for the most part. There's cryptography and stuff, but that's an accident. Okay, so now here we're going to add 3 times the first row to the third row. So 3 times the first row added to the third row, and keep the others the same. Oops. Let's use consistent colors. So add 3 times the first row to the third row. Keep the second row the same. Keep the first and second rows the same, I should say. Keep the first and second rows the same, and then add 3 times the first to the third. So then 3 plus 1 is 4. -3 plus -7 is -10. Right? Sorry, I really don't mean to insult anybody's syllabuses. I'm just saying, you can learn math for fun, and you can learn on your own. You don't have to follow a syllabus. Just hang out here. You'll learn a little bit of math just for fun. Because it's beautiful, because it's fun. It's nice. Like, dude, it's better than scrolling TikTok. You know what I mean? Let's keep the first row the same. Let's multiply the second row by a -1. Now, we'll be a little faster if we do it a little different. Let's keep the second row as it is. Keep the second row the same. So these elementary matrices mean just modify 1 row at a time. And each time we're either like interchanging, like rewriting. Bro, I think most of my audience is from India. I do think so. Dude, I absolutely do think so. Which is an amazing thing about YouTube. I love it. Like, I get to reach an international audience because I have free time during the day because I'm unemployed. I get to, like, hang out with people around the world while I practice guitar and I practice math. It's amazing, dude. It's amazing. Yo, go to sleep. It's 3 a.m. Don't watch me at 3 a.m. you can watch the VODs tomorrow at some point. Like, dude, you can always watch the VODs, but dude, get to bed. Y'all, you found the right channel. If you're watching a weirdo practice math and study math on the internet at 3 a.m., dude, that is so cool. Like, you can't sleep because you're watching somebody study math. Like, that's hilarious. I love that. That's amazing. Thank you. Okay, so what we're gonna do is add 2 times the second row to the third row. And then that way, now we will have 0, 2 times the second row to the third row, 10 plus negative 10, y'all, boom, not invertible. 2 times the second row to the third row. I don't even need to write anymore. We were unable, I said earlier, like, if we can, if it's possible, we're gonna try to get to the identity matrix, but it's not always possible if to have reduced row echelon form have the identity on the left. We ended up with a row of zeros over here. So, done. I don't even need to be writing any of these down. In this case, A inverse does not exist. Doesn't exist. All right, done. That was Frale 156. I feel pretty good about that. I don't need to check with ChatGPT or anything. We are all nerds. Yeah, dude. High school students who study maths at 3 a.m. Now it's my chemistry practical at 7 a.m. Dude, if you have chemistry at 7 a.m., you better go to sleep right now, dude. Y'all, no joke. Like, I feel like a bad influence if y'all are watching me instead of going to bed. Dude, I'm such a bad influence, apparently. But like, dude, sleep is more important than anything. Like, get enough sleep. You're going to like I can't stress that more. Like, sleep is a superpower. If you can get to bed on time and sleep well, like, sleep is really, truly a superpower. So, get some sleep, man. It's been nice hanging out with you today. Thanks for stopping by. 1.6.6. This is about homogeneous systems, subspaces, and bases. All right, 166. It says, determine whether or not this thing is a subspace. So, what's the best letters to use? I like U and V. U is going to be a subset of our vector space V. A subset is a smaller collection within a bigger collection. Like, if we're talking about Venn diagrams, you know, U might be the smaller set and V is the bigger set. So in this case, V is, in this problem, V is R3, three-dimensional space. That's a capital V. And U is the set of all 3 vectors, triples, where X, Y, and Z are in R, are real numbers, and X equals 2Y plus Z. Okay, neat. So, yes, I mean, I think that this will create it's regular for me. Entrance exams are truly demanding. That's crazy. Get some sleep, though, dude. Like, 8 hours of sleep is what you should shoot for. See you tomorrow, love. I think I'll be able to stream again tomorrow. I'll stream earlier, I hope, tomorrow. Good night from India. Good evening to you. All right. Sleep well, y'all. Thanks for stopping by. Okay. So, how do I solve a problem like this? To be a subspace, we need to check two things, A and B. For any, this symbol means for all x, y in our subspace, or in our set U, x plus y is in U, right? And then for all x in U, and for all k in the field, the scalar multiples, for all scalar multiples, then kx is also in U. So this whole book, I think the field is always real numbers. So let's just stick with real numbers for now. But okay, let's check the first property. So if x, we do something like let x be in U and y be in U. Then x1, x2, x3 satisfies x1 equals 2x2 plus x3. Notice that I switch from like component notation to from xyz to, you know what? No, I like the notation that they chose. Let's go with let's choose two vectors, v1 and v2. Then v1, let's say that v1 is x1, y1, z1. And the second vector is x2, y2, z2. I mean, kind of tomato, tomato, but we have like fewer indices this way. Then we have 2y1, oh wait, no, 2x1 well, I'm just going to say, then we want to show that v1 plus v2 is in, also satisfies the properties. Like if I add these two random vectors that satisfy those rules, that after adding them, they still satisfy those same rules. They will. So v1 plus v2 is going to be x1 plus x2, y1 plus y2, z1 plus z2. And we need to check this property. Let's take the left-hand side. x1 plus x2. Well, we know that x1 is equal to 2y1 plus z1, 2y1 plus z1, and x2 is equal to 2y2 plus z2. Because both of them we chose v1 and v2 such that x1 equals 2y1 plus z1, etc. Like, since they were in the subspace, in the subset U. Now, rearranging, we have 2y1 plus y2 plus z1 plus z2, and then voila. So then, like, we could kind of call this like x3 equals 2y3 plus z3, right? So, yes, that shows that if you take two vectors in the subset and add them together, then the subset is closed under vector addition. This one is about closure under scalar multiplication. And this one is also going to be fairly easy. Take x, y, z in U, then and take k to be any real number. Then k times x, y, z is kx, ky, kz, and we need to check if this still holds the property. Kx is the same as k times 2y plus z, which is equal to 2 times ky plus kz. Therefore, kx, ky, kz satisfy the properties of U. So then also known as like kv is in U. K times whatever we call that vector is also in U. Hey, what's up, SR3175? You're from India. Go to bed, dude. Go to bed. Where are you from? What's up, y'all? What's up? I'm from the US. And love, I have a relaxing game for you. Thank you. What game? What game are you talking about, dude? Welcome, everyone. Welcome. All right, so I'm very confident that this is indeed a subspace. Done. (1.7). Now we've got some application problems. My class talking Hindi? I don't know any Hindi, dude. I don't know any Hindi. I wish. You got to teach me. Frale. 1.7 points. Actually, don't teach me, because people have tried to get me to say bad things in other languages, so I'm not going to do that anymore. Application to population distribution. 176. We have the questions. Is a transition matrix? If so, is it normal? So in this problem, A is 0.3, 0.2, 0.5, 0.4, I'm going to go columns, 0.4, 0.1, 0.2. Okay, so if this is C1, the sum of the entries in the first column, 0.7, so the first column adds up to 1. The second column adds to 0.2, 0.2, 0.2, 0.4. Yes, 0.2, 0.2, 0.2, 0.4. So the second column also adds up to 1. The third column, 0010, 0010. The third column also adds up to 1. And 0.5, 0.1, 0.2, 0.2. 0.5, 0.1, 0.2, 0.2. The last column also adds up to 1. Alright, I'll say it. This feels risky. Bai So Jiao. Bahai So Jiao. I hope that you didn't just get me to say something terrible. I trust you. I trust you. I don't have Hindi installed on my computer. Alright. Okay, there you go, dude. Go to bed. Go to bed. Sleep. Go to sleep. Yeah. I believe you. I trust you. Alright. So, yes, this matrix is a transition matrix because all of the columns add to 1. All of the columns add to 1, and every entry is greater than or equal to 0. There's no negative numbers in this matrix. So every entry is non-negative, and the columns add to 1. So yes, it is a transition matrix. Part B, it's normal if there is some number such that AN has no zero entries. So I think that we can see that the third column is always going to have zeros. 0.3, 0.2, 0.5. No, that's not true. So if I take the dot product of this and this, that's going to be something non-zero. I'll give like a little greater than 0. Oh, wait. But that's not the important one. What matters is the dot product with this column. So in that column, this entry, that entry will be 0 because we have a 0 in that component multiplied by that 1. Yeah, that entry is going to be 0. Same thing. Yeah, for all n, it is not regular, because for all n, we're going to have that third column is always going to have is always going to be 0, 0, 1, 0. For all n, for all positive powers of this matrix, we'll always have this column 0, 0, 1, 0. So, boom. Not normal. This thing is not a normal matrix because it will always, because that third column is always has zeros. I could say specifically A13 equals 0. And so does A23 and A43. These are always going to be 0 for all n. Okay, good enough. I feel like that was just like a little squishy in its clarity, but you know what? You know, it's good enough as a hobby right now. 1.8. Last problem. Last problem for today. Frale. 1.8.5. How many errors can always be detected using this code? This is about applications to binary linear codes. This is an optional section. So our the 6.3 linear code C with standard matrix G 1 0 0 0 1 0 0 0 1 You know, I feel like I've solved this problem before, but I didn't cross it out, so 1 0 0 0 1 1 1 0 1 0 1 0 1 1. Okay, so I'm not going to give an introduction to what this is talking about, but we're talking about code checking, like parity checking of It's kind of like if you write down a typo, think of like typing in your credit card into a website. There's all sorts of like little cool rules that say that numbers should add up to certain things. Like the number of even numbers matches the number of odd numbers. Kind of. It's not exactly that, but things like that. If your credit card number doesn't follow the expected structure, the expected rules, then the system, the website can detect that you made a typo. So that's what this section is about. They're called, I keep mixing up two names, Huffman coding, right? Isn't this called Huffman coding? Hamming different distances. Hamming self-correcting codes. Huffman encoding is something different. Hamming distances and hamming codes. All right. So this matrix says that if I have a binary number x1, x2, x3, x4. Oh wait, no, x1, x2, x3. Then we can add these extra bits, x4, x5, x6, where x4 is equal to x1 plus x2, x5 is x1 plus x3, and x6 is x2 plus x3. Okay. Then what this is asking is this is going to be a number of expected numbers in the two-dimensional. So we write B to mean binary numbers sometimes. In B6. But it's actually in the subset. There's only some numbers that are expected, and that subset is a subspace of B6. So then, if the question is, how many errors can be detected using this code? I forgot to actually write the actual problem. What's the actual question? How many errors can be detected using this code? So this is like saying, like, take a vector x in the code, or better yet, take a vector that's not in the code. How many vectors are not in the code? Well, the number of vectors not in the code would be the size of the universe minus the size of the code. Like if we think of Venn diagrams, right? If this subset C is part of the bigger set B6, that what we're asking is how many numbers or vectors are outside of C. Well, the size of B6 is each entry is either 0 or 1. So this is going to be 2 to the 6th. And the size of C is going to be every element in C corresponds to one unique vector in B3. So I'm actually going to say that this is the size of B6 minus the size of B3. And this is 2 to the 6 minus 2 to the 3. This is 64 minus 8. This is 56. 56 errors can be detected. This is an odd numbered problem, so I can check the back of the book. And it's an odd numbered problem, number 5. Yeah, note that each xi appears in at least 2 parity check equations. Wait, what? And that for each combination ij of positions in a message word, some parity check equation contains one of xi, xj, but not the other. As explained following equation 2 in the text, this shows that the distance between code words is at least 3. Consequently, any 2 errors can be detected. I misunderstood what this meant, what this question was asking. I misunderstood its phrasing. Let's see. Okay, that's interesting. All right, I misunderstood this problem. I think I was kind of answering the other thing. How many errors can always be detected using this code? So what it's actually asking is if you flip 1, 2, or 3 bits, then would it be detected? How many errors can, like in a single transmission, how many errors can be detected? I misunderstood the question completely, but what I said made sense in how I interpreted the question. How many errors can always be detected using this code? I'm trying to figure this out without I already peeked at the answer. So, So let this be in so x4 equals x1 plus x2, x5 equals x1 plus x3, and x6 equals x2 plus x3. So I think that this is the key to figuring this out. So if one of these numbers was flipped, then this parity check would be wrong, right? But if for this first equation, for this first parity check to still be valid, we need two of them to be flipped. But if one was flipped, then like now equation 2 and equation 3 are now incorrect. So to make equation 2 correct, then we need to flip another bit. So we would not detect an error in flipping the first, the second, and the third. Like if we flip 3, then we would not detect that error. So then whatever the answer is, because this is asking how many can always be detected, it said can always be detected, then the answer is going to be less than or equal to 2. Can we always detect? If there's one error, then certainly if one bit is flipped, then these parity check equations would not be satisfied. If one is negated or flipped, if one is negated, parity check with xi would fail. With 2, to satisfy the parity check with xi negated, some xj also needs to be negated. A second one does. Then the other parity check with but not xi will fail, right? Because this one has 1 and 2, right? But then this one has 1 but not 2. This one has 2 but not 1. So if both of those are flipped, then these other equations would fail. So so C always detects 1 or 2 errors. QED, roughly. QED. That means we're done in math. Thanks for watching. I'm gonna go. I think I'm done for today. We did a problem from every section in chapter 1. And I think we got that one. I think I finally landed on the general idea in that problem. So now that I totally misunderstood the way that the problem was stated, but what I answered made sense otherwise. All right. Thanks for watching. Bye, everyone. I gotta go. Bye. Next time we'll work through chapter 2 again. All right. Cheers. Bye.